Hello, thanks for joining me. Today I'm going to be looking at Pythagoras' theorem, but not in a geometry aspect, but from a number theory point of view. So firstly, what is Pythagoras' theorem? It says if we take any right angled triangle, okay, we call the longest side C, that's the right angle, and the two shorter sides A and B, then we have that A squared plus B squared equals C squared. And that holds for any right angled triangle, which is quite cool. But this is a geometry sort of side of things. I'm not going to be looking at that today. I'm going to be looking at a number theory problem, which is very, very related. So firstly, we say that a set of three positive integers, a, b, c, is a Pythagorean triple if it satisfies Pythagoras' equation, a squared plus b squared equals c squared. So for example, 3, 4, 5 is a Pythagorean triple. And just to check that, 3 squared, that's 9, 4 squared, that's 16. When I add them up, I get 25, and that is 5 squared. So 3, 4, 5 is a Pythagorean triple. Okay? But what we can do from that is we can actually generate infinitely many Pythagorean triples. So the natural question to ask is, are there infinitely many Pythagorean triples? And this sort of algorithm tells us there is. Take 3, 4, 5, which is 1, and then multiply each number by n, where n is any number you want. So for example, if I multiply by 2, I get 6, 8, 10, and that is also a Pythagorean triple, and we can check that 6 squared is 36, 8 squared is 64, 36 plus 64 is 100, which is 10 squared. And in fact, I can do this for any number. Here I multiply by 2, but I can multiply by n, where n is any positive whole number, and I get another Pythagorean triple. And just to check that, if I do 3n squared plus 4n squared, that's 9n squared, that's 16n squared, that's going to give me 25n squared, that's just 5n squared. So I can generate infinitely many Pythagorean triples this way. So that's sort of a boring problem. But if we add this condition, we talk about primitive Pythagorean triples. So we say a Pythagorean triple is primitive if the greatest common divisor of A, B, C is 1. So in this case, we have 3, 4, 5. Their greatest common divisor is 1. There's no number, there's no positive whole number which divides 3, 4, and 5 other than 1. And that eliminates this sort of cheating, so to speak. We can't just multiply by 2 or by 3 or by n, because here, each of these numbers here share the number 2 as a factor. Each of these numbers here share the number n as a factor. So a more interesting question to ask is, are there infinitely many primitive Pythagorean triples? And the answer is yes, and I will prove that today. Okay? So, let me just rub this all up, and we'll prove it. So, let's start with a primitive Pythagorean triple. So suppose ABC is a primitive Pythagorean triple. Okay, so case 1. AB even. So A and B are both even. Well then, because it satisfies Pythagoras' theorem, which is this, A is even, so A squared is even. B is even, so B squared is even. So that means that C squared is even. But if C squared is even, then that means C is even. Okay, so if A and B are even, then C is even. But then A, B, and C all share common factor 2, which means that the GCD of A, B, C is greater than 1, i.e. they all share common factor at least 2, and hence greater than 1. So this doesn't count. This is not primitive, because we can divide A, B, and C by 2. Okay, now case 2. A, B, both odd. Now this doesn't work either, and I'm going to prove that. If A and B are odd, then because they satisfy A squared plus B squared equals C squared, well, A is odd, so A squared is odd. B is odd, so B squared is odd. So odd plus odd, odd plus odd is even. So C squared is even, but then that means C is even. So AB is odd and C even. Well, A odd, that implies that A is 2L plus 1 for some L, an integer. And B is odd, so B is 2m plus 1 for some integer, and C is 2n for some integer n. Okay, so then putting this back into Pythagoras' theorem, a squared plus b squared equals c squared, we get a squared, which is 2l plus 1 squared plus b squared, which is 2m plus 1 squared, and that equals c squared, which is 2n all squared. Now, let me expand this. I get 4l squared plus 4l plus 1. Here I get plus 4m squared plus 4m plus 1. And on the right hand side I get 4n squared. Now, if I look at the left hand side and look at it mod 4, i.e. what is the remainder of this left hand side when I divide by 4? Well, this thing here is divisible by 4, this thing here is divisible by 4, this thing here is divisible by 4, as is this thing here. So the left hand side, when I divide it by 4, all these things here will give me integers. So I'm only left with the 1 plus 1. So the left hand side is 2 mod 4. Okay, so in other words, the left hand side can be written as 2 plus 4 times lambda, where lambda is l squared plus l plus m squared plus m, but in particular lambda is a whole number. 2 plus 4 lambda, and the right hand side, that's just 4n squared. But then this is a contradiction, because I can write this then as 4n squared, 2 equals 4, that's really rubbish handwriting, 2 equals 4n squared minus lambda. Remember, n squared is an integer, lambda is an integer, so n squared minus lambda is an integer. So the left hand side is 2, and the right hand side is 4 times an integer, so the right hand side is divisible by 4, but it equals 2, but 2 isn't divisible by 4. So this is the contradiction. So case 2, we can't have, so a and b both can't be odd. So the only other option is that a is one of a and b is odd and the other one's even. Okay, so let's clean this up. Okay, so we have that one of a and b is odd and the other one is even. Okay, so I've written here a is odd, b is even, and c is odd. The reason I've written that is because if ABC is a Pythagorean triple, then so is BAC. I can swap the roles of a and b. To see that, so suppose a squared plus b squared equals c squared. Well, then if I swap a for b and b for a, I just get b squared plus a squared. Well, that's the same as a squared plus b squared. And that, of course, equals c squared. So b and a is also a Pythagorean triple. So 3, 4, 5, for example, is a Pythagorean triple. But so is 4, 3, 5. So I can swap the first two terms, a and b, and it won't change anything. So I may assume, without loss of generality, that a is odd and b is even. Because if it was the other way around, then I can just swap them. So if I can work out all the ones where a is odd and b is even, then right at the end I can just swap the roles of a and b to get all the other ones. So I assume, without loss of generality, a is odd and b is even, and then looking back at Pythagoras' theorem, we get an odd number squared, which is odd, an even number squared is even, odd plus even is odd, so that means c squared is odd, which means c is odd. Hence, a odd, b even, and c odd. Okay? So now, looking back at Pythagoras' theorem, a squared plus b squared equals c squared. I'm going to subtract a squared from both sides, so I get b squared equals c squared minus a squared, and I can complete the square and write this as c plus a times c minus a. Now what I'm going to do is divide both sides by 4, so I get b squared over 4, that's the same as b over 2 all squared, and then that equals c plus a over 2 times c minus a over 2. Now, I'm going to make the claim that c plus a over 2 and c minus a over 2 share no factors, or the only factor they share is 1. Their GCD is just 1. And I'm going to make that claim and I'm going to prove it. So suppose d divides both this number and this number. So d divides c plus a over 2 and d divides c minus a over 2. Okay, well, for example, I make the claim that d divides these two numbers added together and also this number minus this number, and that holds for any sort of relation like this. So for example, 3 divides 6 and 3 divides 9, so 3 also divides 9 plus 6, and it also divides 9 minus 6. 9 plus 6 is 15, 3 obviously divides 15, and 9 minus 6 is 3, and 3 divides 3. Okay, so this holds for any sort of relation like this. So if I add these two together, I get that d divides c plus a over 2 plus c minus a over 2. Well, the a over 2's will cancel, and I'll be left with c over 2 plus c over 2, which is just c. Okay, if I do this minus this now, I get that d divides the c over 2's will cancel, and I'll get a minus 2 minus minus a over 2, which is just a. Okay, so d divides c and d divides a. Well, then that means I can write d equals lambda c for some lambda, an integer, and then d equals mu times a for some integer mu. But then putting that back into... Oh, sorry. I've written this wrong. This means I can write c as lambda times d for some integer lambda, and I can write a as mu times d for some integer mu. But then putting that back into a squared plus b squared equals c squared, I get a squared, which is going to be mu d squared, plus b squared equals c squared, which is going to be lambda d all squared. So just rearranging this, I get b squared equals d squared, lambda squared minus mu squared. Okay, and then if I square root both sides, I get b equals d times the square root of lambda squared minus mu squared. But in particular, that means that d divides b as well. But then we've got a number that divides a, c and b, but because it's primitive, it means that d must be 1. i.e., any factor of c plus a over 2 and c minus a over 2 must be 1, and hence the greatest common divisor of c plus a over 2 and c minus a over 2 is 1. Okay, a bit long-winded, but it's important, as we'll see just now. Okay, so we've written b over 2 squared as these two things here. Now, notice b was even, so b divided by 2 is still an integer, and obviously when I square an integer, I get a square number. Now, since these two numbers here are co-prime, i.e. they share no factors greater than 1, and the product is square, it must be that each of these numbers are square numbers. Okay, so that means I can write c plus a over 2 as k squared, and c minus a over 2 as l squared for some k and l. And also note in particular that k must be bigger than l. Okay, so let's notice then that if we add these two together, I get that c, because c plus a over 2 plus c minus a over 2, that's c over 2 plus c over 2, which is c. That's going to be k squared plus l squared. And then a, which is going to be c plus a over 2 minus c minus a over 2, is going to be k squared minus l squared. And we also have b from this, because b over 2 squared equals k squared times l squared. So it must be that b is then, so b over 2 equals k times l. So multiplying both sides by 2 gives us that b is 2kl. Now firstly, some conditions on k and l. K is bigger than l, as we said there, but also k and l can't share any factors, because if they did, then k squared and l squared would share factors, k squared minus l squared. So sorry, if use the same argument as before, losing my words there, if d divides k, again, well, d is a different d, let's say d tilde, d divides k and d tilde divides l. Let's get rid of all this. So d tilde divides k and d tilde divides l. Then we have that this thing here is d, so that k equals d tilde times some lambda tilde, and then l equals d tilde times some mu tilde, where these are all integers. If I just plug this then back in here, I get that c is equal to k squared plus l squared, which is going to be d tilde squared times lambda tilde squared plus d tilde squared plus mu times mu tilde squared, which is going to be d tilde squared lambda tilde squared plus mu tilde squared. In other words, c divides d tilde squared. Similarly, a will divide d tilde squared and b will divide d tilde squared, but obviously because they're primitive, that means that d tilde squared must be 1, and hence d tilde is 1. And hence k and l don't share any factors, i.e. they are co-prime. Okay, so that's another condition on k and l. So we have that k is bigger than l as one condition, and k, l are co-prime. So their greatest common divisor is 1. And in fact, that is enough to say that these are all the primitive Pythagorean triples. We don't have to do any further analysis about k and the special case where k is odd and l is even. This is actually the final result, and I'm going to prove that. So let me just claim what I'm proving. Let me rub all this off. My board's about to fall. Right, so my claim is this. So ABC is a primitive Pythagorean triple if and only if it is A, B and C take the form. Oh, and I should say the case B is even, so B even. So B is even, A, B, C take the form. A equals k squared minus L squared, B equals 2KL, and C equals k squared plus L squared, where, remember the two conditions I had here, k is bigger than L, and k, comma L, they share no factors. Okay? And one more thing actually. A condition I didn't mention was that k and L have to have different parities, i.e. one's odd and one's even. And the reason for that is sort of a similar thing here. If k and L had the same parity, then k squared and L squared would have the same parity. And you know, if they're both odd, two odd numbers make even, or if they're both even, two even numbers make even. So you get C is even. Similarly, k, you know, if k is k squared minus L squared, it'll be either odd minus odd or even minus even. Either way, you're going to get an even number. So A is even, and then B automatically is even because of the two there. So A, B, and C would be even, which means that it's not primitive. They're all divisible by 2. So K is bigger than L. GCD of K, L is 1, and K and L have different parities. Different parities. Just squeeze that on there. Okay, so now that's the claim. So what we've already shown one direction. We've shown if ABC is a Pythagorean triple, then it must be of this form. Now I want to show the reverse holds, i.e. if A, B and C are integers of this form, then they're a primitive Pythagorean triple. Okay, so firstly let's check that they're a Pythagorean triple. So let's do A squared plus B squared, and hopefully we should get C squared. So A squared plus B squared, well, that's K squared minus L squared, all squared, plus B squared is going to be 2KL all squared. Okay, let's expand this out. We get K to the 4 minus 2K squared L squared plus L to the 4, and plus 4K squared L squared. These two we can bring together. We can write this as K to the 4 plus 2K squared L squared plus L to the 4. Okay, and then this is just, in brackets, K squared plus L squared, all squared, but that is just C squared. Okay, so indeed A squared plus B squared equals C squared. So if we have integers of this form, so K, we choose K and L such that K is bigger than L, the greatest common divisor is 1, and that they have different parities, then A, B, C of this form is a Pythagorean triple. Now we just have to check that it's primitive. In other words, A, B and C share no factors. Okay, and to do that I'm going to show that A and C share no factors. So obviously if A and C share no factors, then A, B and C certainly share no factors. Okay, so let D divide K squared minus L squared, and D divide K squared plus L squared. So we're going to show that D must be 1. Okay, like we've done with the other arguments. Okay, first thing to note is that from the same argument I have that D divides these two, the sum of these two things and those two things subtracted from one another. So if I add these two, I get that D divides 2K squared. And if I do this minus this, I get that D divides 2L squared. Now, because K and L have different parities, i.e. one is odd and one is even, that means that K squared plus L squared is going to be an odd number plus an even number, or an odd number squared plus an even number squared, which is an odd plus an even, which is an odd. So that means that D divides an odd number. So that means D must be odd, because obviously no even numbers divide an odd number. Okay, so D divides, so D is odd. So then looking at this thing here, that means that D divides K squared and D divides L squared. Because the K is, the D is going to come from inside the K squared here and inside the L squared here, because it won't be able to, 2 won't play a role in D, if that makes any sense, because D is not even, D is odd. Okay, so D divides K squared and D divides L squared. Okay, and that means that, one last comment to make. Well, we've used the fact that K and L have different parities to deduce this. Now we're going to use their greatest common divisor. Oh, sorry, we want to show that because their greatest common divisor is 1, we know that the greatest common divisor of their square is 1, i.e. D divides K squared and D divides L squared, but because K and L are coprime, it means that K squared and L squared are coprime, which means that D must be 1. In other words, if D divides K squared minus L squared and D divides K squared plus L squared, it must be that D is 1, and hence K squared minus L squared and K squared plus L squared are coprime, and hence A, B, C are coprime, they share no common factors greater than 1, and hence A, B, C is a primitive Pythagorean triple. So we're done. So just to go over what we have done, we've shown that if we have our B term as even, then A, B, C is a primitive Pythagorean triple if and only if it takes this form. So what's quite nice about this is that means that we can generate not just some primitive Pythagorean triples, but all of them. So if we, for example, consider K is 7, and then L equals 2, so do they satisfy these conditions? Yes, K is bigger than L. The greatest common divisor of K and L is certainly 1, and K and L are different parities, odd, even. Okay, then we have that A is 7 squared minus 2 squared, that's 49 minus 4, which is 45. B is going to be 2 times K times L, so that's 2 times 7 is 14, times 2 is 28. And then C is equal to K squared plus L squared, so 7 squared is 49, plus 2 squared is 4, so that's 53. And in fact you can go and verify that 45 squared plus 28 squared is 53 squared. And I guess one thing to note is, remember what we said at the start, we can swap the A and B's. This is the case when B is even, but obviously we could also have A equals 28, B equals 45, and C equals 53 as another primitive Pythagorean triple. That's it for now. I hope you've enjoyed the video, but yeah, have a great day. See you soon.